Good evening and welcome to today's Tech Talk. It is the topic for today is latest insights on ICS OT security, attack update, the CIE strategy, and the engineering grade protections. Uh, and we welcome Andrew Ginter as a speaker for today's session. So it'll be 1 hour of technical talk by our guest and 30 minutes of Q&A. And uh, just some house rules. Um, if you are driving, kindly stop at a safe place for duration of the webinar. Hope you are aware of your surroundings in your environment. And as mentioned, the session will be for 1 hour, followed by a Q&A. The Q&A questions can be asked by MS Teams, so do not use the chat. And there will be a feedback form that will be shared at the end of session where your feedback will be recorded, and we kindly request you to all share the feedback. And there's also a certificate of participation for today's event. So today's speaker, Andrew Ginter, he is currently working at Waterfall Security. We must have all heard about him. He's quite active and a very vocal proponent of industrial control system cybersecurity, and of one of the world's leading uh, experts and speaker as well. So before Waterfall, he has worked at Hewlett Packard, Agilent Technologies, and at Industrial Defender. And at Industrial Defender, he was instrumental in developing the industrial CM that we all know. Today, it's quite popular, and he's also a author of 2 textbooks on industrial OT cybersecurity. And fortunately, I have a copy of them as well. This is the first books that I read when I got into cybersecurity. And he also co-author of Industrial Internet Security Framework. This is very interesting in its approach, and it was way ahead of its time before other frameworks were developed. And he is also a co-author of UITP report on cybersecurity requirements in rail system tendering. And he is also a regular speaker, which he also co-hosts, called Industry Security Podcast. And he is also a member of various standards body, and active contributor as well. And he has written a lot of articles on best practice and so on. We welcome you, Andrew, to today's Tech Talk. So before we go into session and handover, one can always follow us on LinkedIn, Twitter, and join our community on WhatsApp. So quickly reminding you, all the questions on the MS Teams Q&A do not enter into the chat. So welcome once again, and over to you, Andrew.
Thank you so much for the kind introduction. Excuse me. As my late grandmother used to say, there's no rest for the wicked, so I must be very wicked. If you could, am I going to share my slides here? Are you going to? How's that going to work?
Yeah, whatever is convenient. If you want, I can share it as well.
I can share it. I thought that you had, but that's fine.
Yeah.
Let's do that.
All right.
If I can figure out how to do
no
this
worries.
again.
I will share, and you can start. I think that would be better.
Okay, let's do that.
Yeah.
While right. You're bringing that up, there we go. I had so thank you everyone for joining us. Let me start with that. It's it's a new community that I've only just learned about, so I'm keenly watching the WhatsApp and learning what you folks are up to. Where to begin? We're going to be talking today. This is a bunch of stuff that I've been working on for the last several years, actually, leading up to the next book that I'm writing. I have, a sneak preview, one slide on what's coming in, hopefully October, November of this year. And we're going to start with the threat environment. It's changed in ways that a lot of people haven't been paying attention to. I'm going to, you know, in a sense, the threat environment's the bad news. I'm going to touch as well on a new strategy out of the Department of Energy in the United States, which I'm very interested in, the cyber-informed engineering strategy. And I'm going to lead into, you know, some of the content of the strategy. It's a work in progress, and especially content related to network engineering. So let's begin. If we could move on to the next slide, please. So this section of the presentation is from a report that Waterfall put out a couple of months ago. You can download it on the Waterfall website, the 2023-threat-report. It talks about cyber attacks on the cyber attacks that have physical consequences. So, I mean, there's a lot of threat reports out there, and I read most of them, and I'm frustrated by many of them because they don't say what they're counting. They give us a lot of numbers, you know, but they don't tell us what they're counting. An internet service provider that manages firewalls for industrial customers might say, we defeated 9.3 billion attacks on critical infrastructure last year. And you're going, what does that mean? 9.3 billion. You manage firewalls. Did you drop 9.3 billion packets on the firewall, on the internet firewall for the critical infrastructure customer, and call each of those packets an attack? What does this mean? And most of the time they won't tell us. Some of the times it's confidential data. They can't tell us. You know, some of the time they just won't tell us it, you know, and even if you find out, no, these were actual incidents, you know, some report might be reporting, you know, actual attacks. Well, were they attacks on the IT network? Doesn't say. Were they attacks on the OT network? Did they shut down production? What industries were these? There's so many question marks. So what Waterfall did with this report is we went to sort of the other extreme. We said, let's produce the world's most verifiable, you know, least controversial report. And so we did the research since 2010. We said, let's count deliberate cyber attacks, cyber sabotage attacks, not errors and omissions, okay, not equipment failures, deliberate attacks that caused physical consequences, outages, equipment damage, or worse, in the industries that we understand, which is, you know, I'm not an expert on healthcare. I was really reluctant to do anything with industries I really didn't understand. So we're focused on process industries, especially critical industrial infrastructure and discrete manufacturing, everything from toasters to aircraft parts. So deliberate attacks that caused physical consequences in process and discrete manufacturing industries in the public record. Okay, no confidential disclosures. Every one of these attacks you can verify on the front page of the New York Times. So with those criteria, how many attacks were there in 2010 that met that criteria? If we could go to the next slide, please. There was one. It was Stuxnet. We all heard about Stuxnet. Next slide, please. 2011, there was nothing. 2011, there was a lot of attacks on critical infrastructure back then. Wait for it. You're getting ahead of me. There's a lot of attacks in 2011. None of them caused physical consequences. Okay, they were stealing information. They were defeated. They did not shut anything down. Next slide, please. In 2012, there were two attacks that caused physical consequences. Oh, if we could advance, please. There we go. 2012. Here we go. One of them was a power plant. The power plant was not shut down. The power plant was already down for maintenance. But malware got into the control system and delayed the startup of the plant by 3 weeks. So we counted that as a physical consequence. There were gas stations in Iran that were shut down. You know, you go, gas stations, is retail in scope here? Well, it isn't really, but you know, so we did not count attacks on retail infrastructure, even though retail is arguably critical commercial infrastructure. We did not count it, but we did count the gas stations because gas stations are widely seen as the low end, the extreme downstream end of oil and gas. So we said, fine, we'll count it. 2013, next slide, please. There was nothing. 2014, next slide, please. There was one. This was the German BSI reported a steel mill. Malware got in there, massive damages. Never identified the steel mill, but it was in the public record. It was from a report from a credible source, so we counted it. 2015. Next slide, please. There was one. It was the first Russian attack on the Ukrainian power infrastructure. Took down 30 distribution substations. Turned the lights out for 225,000 customers. The lights were turned back on between 1 and 6 hours later. So that's a physical consequence. Next slide, please. 2016, there was one. That was the second attack on the Russian infrastructure. It shut down the power in Kiev, the capital of the Ukraine, for 1 hour because they targeted a high voltage transmission substation. Next slide, please. 2017 was a busy year. You heard of Triton. This was the attack on a Middle Eastern oil and gas facility. Was shut down twice by the attack. It was the same attack. The same attack group was in there. They were stirring the pot. They were sabotaging safety instrumented systems. This is arguably attempted murder. If you sabotage a safety instrumented system and you cause a safety incident and the safety system malfunctions, you put human life at risk. Nobody was injured. In fact, the attackers fumbled the code they were putting into the safety system, and they tripped the plant. The plant investigated and said, I don't know why this safety system tripped. And they brought the plant back up. A couple of months later, the attackers again fumbled and tripped the plant. The engineers at the plant said, what's going on? They sent the safety equipment, Triconic safety equipment, back to the vendor and said, here, your system is broken, fix it. And the vendor found the attack. So that was Triton. Not Petya was, again, Russians trying to attack the Ukraine, but they fumbled. They put Killware, disk erase software into a security update for a Ukrainian tax package that was widely used. Hundreds of victims auto-updated their tax package and wound up with, lots, thousands and thousands of hard drives erased. Physical consequences. Maersk shipping was down for 6 days. Container shipping was down. Merck Pharmaceutical, similar names. Maersk Shipping, Merck Pharmaceutical, two different companies. 4 of their pharmaceutical plants tripped. They lost 4 very expensive batches of product. They filed a claim with their insurer for $1.4 billion US dollars. That's billion with a B, 10 to the 9th US dollars. The insurer contested it, saying this was a nation state attack. It triggers the nation state clause. You don't get coverage. They went to court. The court said, no, the nation state clause says act of war. This was not an act of war. Nobody declared war. Therefore, pay. Zurich, the insurer, appealed. The appeal court sided with Merck. Merck was awarded $1.4 billion. So, big news in 2017. Next slide, please. 2018, there was one. It was a semiconductor fab in Taiwan. Next slide, please. 2019, there was 4. The big name was Norsk Hydro. Norsk Hydro shut down 4, I think it was, sheet aluminum plants. Why is a power company producing aluminum? How does this work? How does this make sense? What happened was that ransomware got into the IT network, and if you're smelting aluminum, it consumes enormous amounts of electric power. If you have electric power at your fingertips, if you have experts who really understand the electric system, you have a competitive advantage smelting aluminum. And so Norsk was smelting aluminum. When the bad guys got into the IT network, Norsk looked around and said, well, what are we going to do? They looked at their OT security program for their power plants, and they said, we're confident of the strength of these programs, and they left the power plants running. They looked at the OT security system for their aluminum smelters, and they said, we're not at all confident of the aluminum smelters. And so they went and they turned off all of the computers in the smelters, and they operated the smelters by hand. No physical consequence. The sheet aluminum plants, they said, we're not at all confident of the security program, and these plants are so heavily automated, we cannot operate them by hand. Therefore, they shut the plants down. 4 plants down, physical consequence. Next slide, please. 2020 was a busy year. I think all of this, all except one, no, I think all of it was ransomware. 18 incidents affecting, dozens and dozens of physical sites. Everything from a lot of manufacturing, but there was shipping stopped at ports. Honda went down for 4 days. They lost, I think, something like 1,000 or 2,000 vehicles that could not be produced. They were behind on their production at the end of the quarter. A brewery went down. Beer could not be produced. So that was 2020. Next slide, please. There was even more in 22. Almost all of these were ransomware. Colonial was the big name. Everyone heard about the Colonial Pipeline going down. Massive lineups. 40% of the gasoline that was consumed in the American Northeast came through Colonial. There was one hacktivist attack here. Oh, hang on. My camera's going wonky. There we go. There was one hacktivist attack here. This was the Iran signage attack, most of the way down the left-hand side. Hacktivists got in, changed the signage. You might ask, how does signage cause a physical consequence? Trains could not run. Passengers could not find their trains. All of the signage said the trains are canceled, the trains are delayed, don't bother going to the station. Chaos for hours until the signage could be repaired. Was not an attack on OT. It was an attack on IT. The signage systems were on the IT network, but it had physical consequences. The trains could not run. Next slide, please. Last year was a very busy year. There was cyber attacks that impacted oil and gas. That's the bold stuff on the upper left. These were 3 or 4 oil terminals, ports that could not ship oil because of, or could not receive oil because of this cyber attack. Bridgestone, a brand name, went down. 23 plants went down for 10 days. Massive impact. Agco, in the middle of the right-hand side, you might say Agco. What kind of brand name is Agco? Agco produces Massey Ferguson farm equipment. They lost 2 weeks of production right in the peak buying period, where most of the Northern Hemisphere was planting. Next slide, please. It goes on. Profete on the right-hand side, halfway down, went out of business. This was a bicycle manufacturer. Now, you can argue, did the ransomware attack cause them to go out of business? Were they not in trouble before this? And the short answer is, I haven't dug into it that much. The short answer is that in the insolvency filing, in the court filing, they said the ransomware was a material factor in the bankruptcy. Next slide, please. And sort of the big name was Copper Mountain mining in northern Canada. Was a huge strip mine that was shut down for 5 days. So 57 incidents. Next slide, please. This is looking like exponential growth. If you average out the exponents since 2019, we're looking at increasing by 2.4 or 2.45 times every year. At that rate, this year, we're still counting. This year, we're going to see 130, 140, maybe 150 of these attacks, impacting probably 250 industrial sites. Next slide, please. The world has changed. In the last decade, between 2010 and 2019, I conclude that cyber, incidents on, the cyber risk to physical operations was largely theoretical. There was a lot of attacks that caused no consequences. There was a lot of governments worried about attacks that could cause consequences. Forward-looking organizations were doing something about the problem, but sort of the man on the street, everybody else was looking at it saying, is this real? In 2019 and 2020, this changed. It changed from a theoretical problem to a very real problem that's more than doubling every year. Does anyone believe we had 57 incidents last year? We're predicting 130 this year. Does anyone believe that we're ever going to go back to a year like 2018 where there was one incident? I don't. The world has changed. Most of this is ransomware. Last year, 10% of it was hacktivists. How does ransomware affect operations? It can do it in only three ways. It can target the OT systems directly. The Snake ransomware does this. It's got code in there that understands OT systems. This was the ransomware that hit Honda several times and shut down operations. The second way that ransomware can affect physical operations is what's called abundance of caution shutdowns. This was the Colonial scenario. Ransomware is on the IT network. People look at their OT security program and say, we cannot trust the strength of this program to protect physical operations. Therefore, we must shut down. This was the Norsk Hydro, brain blank, the Norsk Hydro sheet aluminum plant scenario. The third way, and this happens a lot in my estimation in transport. Now, when I say my estimation, some of this is guesswork because we are relying on public reports. In the report, every incident we count has a link in the appendix where you can go verify the details of the incident in the public record. And so the public record is usually produced by reporters, and they don't often give you a lot of detail. It's, a lot of times the companies just don't release the detail. So we don't have all of the detail we'd like. But as far as I can tell, a lot of the incidents in transport especially happened because ransomware crippled the IT network. And physical operations depends to some extent on facilities in the IT network. And I've got a longer example on this later in the episode if we get to it. So if this trend continues, how much trouble are we in? If this trend continues, we expect to see in the year 2027, 4,500 attacks affecting 15,000 sites. The world has changed. Next slide, please. So that was the bad news. The good news is that there's something new in the world for defenders. And what's new in the world is a strategy that the US Department of Energy has put together called cyber-informed engineering. I call it security engineering for short. What is it? Well, the classic example is let's say each of us is a technician in a coal-fired power plant. How does a coal-fired power plant work? You've got, a large plant has 6 generating units. Each generating unit has a conveyor that takes powdered coal dust, that into a furnace, blows it into the furnace. The dust ignites. It burns almost instantly. In less than a second, the dust is consumed. It's turned into heat and, of course, carbon dioxide and water. And the heat heats a massive 5-story boiler. It's a huge reservoir of water and steam. Produces steam. The steam goes into a turbine. It turns the pressure of the steam into rotational energy. The turbine is connected to a generator, which, they rotate together. You produce electricity. Your job as the technician is to manage the boiler. Okay, boilers corrode, they need to be tested, they are instrumented, the instrumentation needs to be calibrated. Your job is to keep these 6 boilers working properly. And if a cyber attack gets into one of the furnaces and overheats the boiler, and the boiler explodes, and each of you is within the kill radius of the blast, you're dead. You never see your kids again. How would you like to be protected against that, the consequences of that kind of cyber attack? Would you prefer a mechanical valve with a pin so that it's pressed against a hole in the boiler, and if the pressure in the boiler becomes too great, it forces the plate against the pin breaks, the steam escapes, and there's no explosion? Would you like an overpressure valve, or 3 of them, because these things do wear out? Or would you like a longer password on the PLC controlling the furnace? I would like an overpressure valve, thank you, or 3 of them. So here's the thing. Look at the NIST cybersecurity framework. Look at IEC 62443. Look at any of these standards and best practices on the cybersecurity side. Where is the overpressure valve in 62443? Where is it in the NIST cybersecurity framework? It's not there. This is not a cybersecurity mitigation for cyber risk. This is an engineering, a mechanical mitigation for cyber risk. So this is a whole field of protection that we have been blind to as practitioners if all we've been looking at is cybersecurity. None of this is, little of this is new. It's not that we're inventing all of this. And if you look at the strategy the strategy is not a recipe how to do security engineering. The strategy says we need cyber-informed engineering. What we should do is create a body of knowledge for cyber-informed engineering and bring the academics, the university professors, the tech school professors on board with it so that they teach this to students. We need, training programs for existing practitioners. We need. It's a plan to create cyber-informed engineering. It's not a recipe how to do it. But none of this is terribly new. Safety engineering, the engineering profession's been doing for 50 years. It's that it has not, these powerful tools have not been systematically applied to the task of protecting against cyber risk. They're systematically applied to protecting, workers' safety against earthquakes, against hurricanes, against tornadoes, against fires and explosions. They have not been systematically applied. They are occasionally. There are people doing, some of this stuff to deal with cyber risk, but it's not been done systematically. But, so none of this is terribly new. This is a strategy, not a recipe. And it's talking about engineering grade protection. What's the difference? What's the difference between engineering grade and IT grade? Well, again, imagine that the engineering profession has figured out how to build a new kind of suspension bridge. I mean, we all remember the Tacoma Narrows disaster, a very long suspension bridge. And this was before the profession had figured out resonant frequencies. And a wind came along and started the bridge vibrating and started, building up a resonant frequency in the bridge. The bridge eventually tore itself to pieces. Imagine that the profession has figured out how to build bridges at 1/3 the cost of regular suspension bridges. Huge savings, but the new approach is riddled, absolutely riddled with harmonic frequencies. On the smallest stimulus, the thing shakes itself to pieces. And so what we've deployed, what the profession has deployed in these bridges is active vibration dampers, computer-controlled dampers, artificial intelligence-controlled dampers, so that the smallest vibration in the bridge is automatically dampened out, so that the bridge does not tear itself to pieces. They've designed redundant power supplies into all of these dampers. They've designed redundant computers. If a computer fails, the dampers keep working. They've got this figured out. How happy would you be driving across this new bridge every day on the way to work? How happy would you be if you knew that the design engineer hoped that if an attack targeted the AI or the computers damping the vibrations on the bridge, hoped that that attack could be detected before it caused physical consequences? How happy would you be driving across that bridge if you knew that the design engineer hoped that if the attack was not detected and got into the computers, the incident response teams could respond quickly enough to prevent physical consequences? How happy would you be knowing that the design engineer hoped that, if the attack, was not detected in time and the response teams could not prevent, the bad stuff from compromising the computer? How happy would you be knowing the design engineer hoped that the response teams could erase and restore functionality to these computers fast enough to prevent the bridge shaking itself to pieces? I would not be very happy doing that. Hope is not good engineering. Hope is not an engineering grade solution. Okay. Hope is not how we build bridges. This is not the expectation we have of the engineering profession. We expect solutions, engineering grade solutions are solutions that work predictably, deterministically, in a way that can be modeled mathematically so that we can determine exactly how reliable this bridge is, how reliable it has to be, how we can build the reliability of the bridge against a target so that it will carry the specified load for the specified number of decades with a very high degree of confidence. Next slide, please. So that's what cyber-informed engineering is. It's under development, but it's going to take 5 years for this initiative to finish. The good news is that we don't have to wait 5 years to use cyber-informed engineering. Most of the techniques in the body of knowledge are already documented. They're just not being used systematically. So Security PHA Review, the middle book here, this is from the ISA. It talks about OSHA process hazard analysis outputs. This is a kind of safety review that has to be done on almost every industrial site certainly in the United States and often in other jurisdictions. Any site that has potentially unsafe incidents that are possible, explosions, fires, whatnot. And what it says is, look, add a couple of columns into the spreadsheet that's the result of the process hazard analysis for the outcome, the boiler explosion in the power plant. For the given outcome, look at all of the ways that outcome can be caused. It can be caused by someone misoperating the furnace by accident. It can be caused by go through all of the list of possible causes. If any of those causes can be brought about by a cyber attack, okay, now we've got to look deeper. If none of the causes can be brought about by a cyber attack, we're done with that. Move on to the next entry. So if any of the trigger conditions can be caused by a cyber attack, now we've got to look at mitigations. And usually there's, a bunch of mitigations. There are overpressure valves. There are alarms that come up on the operator's HMI, and the operator can look at the alarms and say that's not supposed to happen, and turn off the coal dust conveyor. Look at all of the mitigations. If any of the causes are hackable, if all of the mitigations are hackable, now we have a problem. Now we have a condition where, a situation where an unsafe condition can be caused by a cyber attack. The recommendation is, whenever possible, put some unhackable engineering mitigations in place. Don't rely on the alarm and the HMI and the operator. Put something in there, because the alarm server and the HMI can both be hacked. The operator can be deceived. So don't rely exclusively on hackable mitigations. Put some unhackable stuff in there. Countering cyber sabotage, the subtitle is Consequence-Driven Cyber-Informed Engineering. Very, very closely related to the cyber-informed engineering coming out of the DOE. It's the same people involved in both initiatives. Countering cyber sabotage, it documents primarily a risk assessment methodology, but it's got about 4 chapters in there on unhackable mitigations as well. The example they regularly bring up is manual operations. This is what happened in the aluminum smelters with Norsk Hydro. They shut down all of the computers. They operated the system manually. This is what happened in the Ukraine. When the first Russian attack targeted 30 substations in the Ukraine, what did the defenders do? They drove out to the substations. They turned off all of the computers. They took the manual switch and went click and put the power back into the subdivision and carried on. They operated those 30 sites manually until they were confident of the automation once again. So that's CCE, Consequence-Driven Cyber-Informed Engineering. And the last one is Secure Operations Technology. This is my book from a few years ago. And it is not a book, I work for Waterfall. This is not a book about Waterfall. This is a book about Waterfall's customers. Okay. We work with the world's most secure industrial sites. They ask different questions. They get different answers because they ask different questions. They look at security differently. This is about their perspective. And a lot of it has to do with an emerging field called network engineering, which I'm going to talk more about. But all of these are examples of approaches for engineering grade solutions for cyber risk, not cybersecurity. These are engineering grade solutions that are outside of cybersecurity, but they address cyber risk to physical operations. Next slide, please. So, I was going to talk a little more about network engineering. What is network engineering? Let me give you just one example of network engineering. This example is from EPRI, the U.S. Electric Power Research Institute. They were given a job by their funding, the people who give them problems to work on, the electric industry in the United States. The electric industry said, look, we have these steam turbines, hundreds of tons of rotating steel. Friction is the enemy of all rotating equipment. Things wear out. Vibration is the symptom of wear, of friction. And so, all of these massive turbines are instrumented with vibration sensors. And in the modern world, the vibration sensors all have a CPU. This is the sort of the classic use case for the industrial Internet of Things. This is the killer app for the industrial Internet, predictive maintenance. All of these sensors are designed to send information straight out to the Internet, to the vendor that manufactured the turbine. The vendor is the world's expert on these turbines. They build these turbines. The vendor will give us a warranty on the turbine only if we instrument the turbine and send the vibration information to the vendor 24/7. They will give us a support contract for the turbine only if they can get that information and use their expert system, use their expert people to predict when the turbine needs maintenance. So the question was, these vendors are telling us we're supposed to connect the deepest parts of our control system straight out to the Internet through 7 layers of firewall. This does not seem like a good idea. The worry is what happens if a bad guy gets into the vendor, like they did at, the Russians got into the Ukrainian tax package. There's lots of industrial vendors out there. Some are well defended. Some are going to be poorly defended. How can we use this industrial Internet without opening us up to an attack where the vendor is compromised and the bad guys send, compromised firmware, or they just reach back into heavily defended power plants through the connection out to the cloud? How do we do this? EPRI put their PhDs on it, and they came back and they said, here's how you do it. You get the industrial Internet devices. You do an engineering study of the devices. You convince yourself that these devices are physically not able to control anything. They're truly monitor only. It's not that there's a switch in there, like a software switch that says, I've turned off the ability to control. The device is physically not able to control anything. It's truly monitor only. Okay, we've done that. We've convinced ourselves the device can only monitor. That's all it can do. Put the device on its own network. Do not put it on the control network for the power plant. Put it on the IT network. Put it on a DMZ on the IT network. For that matter, stick SIM cards into these devices. Most of these devices can be put straight out in the internet. Put these devices straight out in the internet. Do not put them on the control network for the power plant. If these devices are straight out on the internet, what's the worst that can happen? The bad guys can confuse the data. They can stop the device from reporting data. What happens if you confuse that maintenance data? Well, it means that you maintain the equipment less than optimally. It costs you money, maybe millions of dollars. This is a business consequence. Okay, you can't destroy the turbine by maintaining it badly. There are secondary sensors. These sensors are less intelligent than the industrial internet sensors. This is why we're using the industrial internet. But if the turbine comes anywhere close to a dangerous situation where the turbine is shaking unacceptably, it's going to be shut down from the control system. Okay, these sensors are not control devices. They are trying to save some money by optimizing maintenance. Nothing that compromises a sensor on the internet can get into the control network. There's no advantage. So here's an example of how to design monitor-only industrial internet networks, how to design the network in such a way that an attacker has no advantage in terms of reaching into the important control network by compromising this internet exposed network. That's an example of network engineering. Next slide, please. In a sense, this is an idea whose time has come. What happened on the Colonial Pipeline? Shut down an abundance of caution, widespread shortages. Next slide, please. Within 9 weeks, there was a bunch of papers that happened. Within 9 weeks, there was a new security directive. The authorities. Step back in the oil and gas industry. What was the first industrial cybersecurity standard ever? It was not 62443. It was not SP99. It was API 1164 from the oil and gas industry, from the American Petroleum Institute. At least the big entities in the oil and gas industry, and Colonial is a big entity. They've been leaders in cybersecurity since the very beginning. Government authorities figured, these people had this under control. There were no regulations for cybersecurity in pipelines until Colonial. 9 weeks later, the authorities said, you apparently don't have this under control. Bang, new regulations. What's in the new regulations? There were 3 versions of them. They're all very similar. A lot of it is predictable. You need to have passwords. You need to change the passwords. You shouldn't be giving admin passwords out to everybody hither and yon. You should have multi-factor, at least on your remote access, if not everywhere else. You should have, intrusion detection and on and on. It was really quite predictable. The first versions were kind of strict and really did not take some of the constraints of industrial systems under consideration. The third version is out now, the 02C. And it's got some flexibility in there. It says, I know that some of your systems, it's hard to change the passwords. If you can't change the passwords, you are required to change the passwords. But if you can't change them, well, then you have to document, send the TSA a report of all of the systems, all of the computers you can't change the passwords on, and why you can't change them, and what you're going to do about this risk, because the fact that you can't change the passwords doesn't make the risk go away. What are you going to do to address this threat to reliable operations? So it's a little more flexible, but in a sense, most of it was not a surprise. Next slide, please. But I read it and I was surprised by some stuff that sounded to me like steps towards network engineering. The standard said your goal with an OT security program, your goal is to prevent operational disruption, to keep the pipeline running at necessary capacity. Necessary wasn't defined in the regulation. I assume it means necessary to society. You will keep the pipeline running at necessary capacity, even if the IT network is compromised. I thought, what was interesting to me is that that's the first time I've heard that goal stated, first time I've seen it stated by an authority in writing. To me, this was always the implied goal of every OT security program on the planet, but nobody ever wrote it down. Here they wrote it down, said, this is your goal, make it happen. And they said, here's how you do that. On the very bottom, isolation controls. They said, if bad stuff gets into your IT network, you must have a way to physically separate your IT and OT networks so that your pipeline can keep running at necessary capacity, indefinitely, in spite of the compromised IT network. They said, to bring that about, you're going to have to identify all of the ways that operations depends on IT. Because if your operations depends on a facility on the IT network and that facility is crippled, now your operations are crippled. You've got to identify all those dependencies and get rid of them. And if you can't get rid of them, you have to report them and explain to us in one-syllable words how you're going to keep the OT system running, even if the IT system that OT needs has been crippled. In particular, they said trust relationships are extremely dangerous. Get rid of them. And again, if you can't get rid of them, you have to document them and explain in one-syllable words. So get rid of the trust relationships. What is trust relationships? That's a fancy word for Active Directory. You cannot have the IT Active Directory system manage accounts that OT uses, because that's a classic attack pattern. The bad guys get into Active Directory on the IT network. They create accounts on the OT network that have universal privileges. They log into the OT network through the firewalls, and they do what they want on the OT network. That's unacceptable. You can't have that kind of trust. So these are all, and there was a whole bunch of other measures. It was all about the IT-OT interface. These were sort of the new focus, was the IT-OT interface. Why is the IT-OT interface so important to this authority and to many others? This is sort of a classic example of what I'm seeing in the industry. Next slide, please. What I see here is a trend towards network engineering. A lot has been written about the difference between IT networks and operations networks. A lot has been written about how hard it is to change passwords, how hard it is to put passwords anywhere, how hard it is to patch things, how hard it is to put antivirus on these PLCs that don't even have an operating system that supports antivirus. It's hard to do. That was sort of, the first generation of advice we got said, and this was back in the day where there was no OT security experts, or was almost none. So, don't read this as criticism. I'm grateful to the IT people who came into the industry, in the 2003, 2004, 2005, and helped us out with the first generation of advice. They said basically, do OT security the IT way. I know it's hard. Try harder. Invent a way to do this IT stuff on the OT network. And a lot was written about the difference between IT and OT in terms of how hard it was to apply IT stuff. The second generation of advice that came out in 2016, 2017 started saying, it's not just that it's hard to do IT security on OT. That's not the essential difference. The essential difference is that on OT networks, we're not protecting the information. We're protecting safe operations. We're protecting physical operations from information, because all cyber attacks are information. And that generation, sort of the late 2010s advice came out. NERC-CIP defines how important their networks are entirely in terms of worst case consequences. Okay, physical consequences. The French ANSI standards defined networks almost entirely in terms of consequences. The more recent standards, they're all talking about the difference, the essential difference between OT and IT networks. The difference that drives all of the other changes is consequence. Even if we had a magic wand, if we could wave a magic wand and magically patch everything, magically bring all the versions up to the latest version of the operating system, of the applications, everything, magically put antivirus everywhere, even on devices that don't support it. If we had that magic wand, we would still have to manage our OT networks differently than we manage our IT networks, because consequences on many, not all, on many of these OT networks, the worst case consequence of compromise is unacceptable. So we have to do things differently. That difference drives what we see. Next slide, please. This was the topic of my 2019 book. And, I think I've covered all this already. So basically, all cyber sabotage attacks are information. The customers we work with, their objective is not to protect the information. Their objective is to protect physical operations from information. The only way a control system can change from an uncompromised to a compromised state is if attack information somehow enters the system. And so what we see these customers doing is carrying out an inventory, not of the devices in their control network, but an inventory of all of the ways that information is entering the control networks, because every incoming information flow is also an attack vector. And they're putting network engineering and other engineering solutions in place to address all of that incoming stuff. Because think about it. It's great if we have an overpressure valve. It prevents boilers from blowing up in our face. What happens if the attack gets into the furnace and overpressurizes the boiler? The valve lets the steam escape, and the plant shuts down. It's great that we have flare stacks on catalytic crackers in refineries. What happens if a catalytic cracker overpressurizes and the hot hydrocarbons go up the flare stack and we see a massive flare? We are alive. It didn't blow up in our face. Good job. And the refinery shuts down. The first goal with almost every industrial operation I've ever been at, and there are exceptions, the first one is safety. Don't kill anyone. Don't contaminate the environment. Don't put public safety at risk. The second goal is almost always keep the plant running. It's $1 billion investment. Keep it running. And, a lot of the engineering mitigations for safety and equipment protection will shut the plant down. SecOT is a methodology for preventing the attacks getting into the networks in the first place. This is network engineering, and that prevents us from having to shut down these very expensive physical processes. Next slide, please. I talked about the EPRI example. By far the most common example of network engineering that we see being used is the Unidirectional Gateway. I'm guessing most of you folks have heard about this already, so I'm gonna go through it quickly. The NIST 882 standard defines a unidirectional gateway as a combination of hardware and software. The hardware is physically able to send information in only one direction. There's a fiber optic transmitter, a laser. Could we go to the next slide? It's actually got to look under the hood so if you look under the hood at this, there's two circuit boards. There's a fiber optic transmitter, a laser on the left, and there is a fiber optic receiver, a photocell on the right. And there's two CPUs involved. And there's a physical divider down the center of the unit. If you take your finger, run it down the divider, you can verify visually that there is no cross connect inside the unit. There are dual hot swap power supplies on either side. Each of these sides of the unit has their own power supply. Nothing is shared across the unit. The only connection from left to right is a fiber optic cable. If we could go back to the previous slide, that one fiber optic cable on the front of the unit, that is the only connection between the industrial network and the corporate network. You can send information from the left side of the unit to the right side. It's not physically possible to send anything back. There is no laser on the right side of the unit. It cannot. It's not that it will not. A firewall, if it's configured correctly, should not send bad stuff back into your network. Here's a device that is engineering grade. It cannot send anything bad back into the network. It cannot send anything back into the network. The software, in a sense, is where the magic is. The software makes copies of servers. If we have an OPC server, if we have a Pi server on the left side, a SQL server, whatever we have on the industrial network, the software logs in asks that server for all the latest data, everything new since the last time we logged in. Okay, nothing tricky here. We're not reverse engineering anything. We're using programming libraries. We're using passwords and accounts, logging in, saying, give me everything new. We get that snapshot of 5, 10, 20 megabytes of new stuff. We convert it to the weird one-way formats and push it through the weird one-way hardware. And on the outside, the software, because there's a CPU, you saw under the hood, there's a CPU, the software logs into an identical server. If it's pi on the inside, it's pi on the outside. If it's OPC on the inside, it's OPC on the outside. So previous slide once more. Thank you for that. We log into an identical server and we insert the 5, 10, 30 megabytes of data into that server. And now on the IT network, we have a copy, a replica of what's on the industrial network. Every user, every system, SAP, I spent years connecting industrial systems to SAP. Every system that needs the data asks the copy, the industrial copy for the data. They get the same answer as the live system would have given. And nothing goes back into the industrial network. Everything that's allowed to be shared with the IT network is already out on the IT network. And we work with the copy. The two systems are identical except when something bad happens. Ransomware takes over the IT network. What happens? Well, operations continues unaffected. Operations is blind to the chaos that's consumed the IT network. What happens? We detect, respond, and recover. We detect the compromised equipment. We isolate it. We take forensic images for our forensics people to analyze. We erase the affected equipment. We restore from backups. We repeat. It takes days. At the end of days, we have a gap in the data on the IT network. That's okay. Press a button. We call the plant, call each of our plants, have somebody go to the Unidirectional Gateway, press a button on the plant side, and resend the last, by default 6 hours, but press an extra button, send the last week of data. On the receiving side, the gateway software says, just a minute, I've seen this data before, and throws it out until it finds something that is new and fills in the gap, and off you go again. Operations keeps going even when IT's been compromised. This is the point. 2 slides forward. This is a mature technology. There's a lot of software that can make copies of a lot of systems. Next slide, please. This is a network appliance. We're moving to the next slide. This is the user interface slide. It's a network appliance. It has a web-based user interface. No, that's the previous. So one more. There we go. Again, it's a mature technology. It's been around for a long time. It's easy to use. This kind of network engineering is a good fit. It's used in. If we could go to the next slide. We're going to skip this unless there's a question. Next slide. I'm running a little short. This is used in power generation at the IT/OT interface. The connection between two networks with very different consequences of compromise. A reliability critical network on one side, a safety critical network on one side, a business critical network on the other. Next slide, please. It's used in pipelines. A lot of them, especially since Colonial. Next slide, please. It's used in rail systems because what are the worst case consequences if you mess with a railway switching system? You have passenger trains collide. You have mass casualty incidents. This is completely unacceptable. The rail industry is embracing this technology at almost always the IT/OT interface, the boundary between the control critical, the safety critical network, and the business critical network. Next slide, please. I had one more example I wanted to work through here. I'm going to run just a little bit over. Let me, if you folks could, give me just a couple of extra minutes before I start answering questions. This is an advanced topic that came up. I gave some of this presentation at a conference in Singapore recently. An Australian power company, an Australian oil and gas company came up to me and said, I want to dig into the Colonial example. There were allegations. I mean, the Colonial CEO testified under oath, tell the truth, the whole truth, and nothing but the truth, that they shut down the pipeline in an abundance of caution. But there were unconfirmed reports that, yeah, but if they had not shut the pipeline down because of an abundance of caution, they would have had to shut it down because their custody tracking system, the custody transfer system, the billing system, if you like, was on the IT network was crippled and you could not run the pipeline. I mean, the pipeline does not own the gasoline passing through the pipeline. Other people own it. The pipeline transfers the gasoline. It has to measure exactly how much gasoline is being transferred because the owners want to get paid for this. And so this transferring custody of the content of the pipeline is very important. And so the question was, assume that, if the pipeline had not been shut down out of an abundance of caution, assume that there was this custody transfer system. This was an unconfirmed, report, a source that was never identified, not as credible as the CEO testifying, but still, let's look at the scenario because it's a scenario that comes up in transport. It's a scenario that comes up in a lot of different systems. In transport, it's container tracking. The IT systems that track where every container goes. It does no good if the crane works and you can take the container off of a ship and put it on the truck. It does no good doing that unless you can tell the truck where to take the container. And that container tracking system is almost always on the IT network. If you cripple it, this is what happened to Maersk. They crippled the container tracking system. And for 6 days, they could not put containers on trucks and take them away. How do we deal with this was the question. So I sat down with these guys and we said, we're looking at it. It's not just a safety critical OT network and a business critical IT network. There's also that container tracking system or the custody transfer system or some system on the IT network that's essential to operations, often in a little DMZ by itself. Next slide, please. How do we analyze this? Well, yes, there's a safety critical network on the left. Yes, there's a business critical network on the right. And that DMZ with the tracking system, with the custody transfer system, that DMZ is reliability critical. If you compromise the container tracking system, you cannot cause an unsafe condition the way you could by, misoperating a crane. You cannot cause an unsafe condition, but you can shut down physical operations. That's a physical consequence we want to avoid. So really, we don't have 2 networks at 2 different criticalities. We have 3 networks. How do we do that? Next slide, please. Well, we can put a unidirectional gateway between the safety critical and the IT network so that the safety critical network continues working unaffected. What are we going to do about the reliability critical network? Well, what we came up with was in these examples, and it depends on the example. A refinery is a different animal from a pipeline, which is a different animal from a container tracking system. But let's just say for the container tracking system, we can what's an acceptable outage for the container tracking system? Couple of hours, 6 hours. If the container tracking system was back up after 6 hours, Maersk Shipping would be back up after 6 hours. Is that acceptable? That's a question for the business. Let's assume that a 6-hour outage is acceptable. How can we make sure the container tracking system comes back in 6 hours? Put it on its own network, put it on a virtual machine, take snapshots of the virtual machine, keep an immutable, a write once, a write only transaction log of the transactions that are running through the container tracking system so that if it's compromised, you can go back to the last known clean state in an hour. The incident response team makes a beeline for this system, erases the current system, restores from backup, replays the transaction logs, and you're up and running again. The reliability consequence has been averted. But that means that a lot of the IT/OT dependency stuff has to apply here as well. We cannot have the container tracking system depend upon the rest of the IT network for operation because we haven't restored. It's going to take a week to restore the rest of the IT network. We cannot have those dependencies. We cannot have shared trusts. All of the rules that apply to the consequence boundary with the safety system also apply to the consequence boundary with the reliability critical system. We need engineering grade protections. We need a way to restore reliably the operation of that system, even though the IT system is crippled. We need network engineering applied to that system. So this is a field that's emerging. This is a scenario that I'm documenting in the new book. Next slide, please. I am not seeing the next slide, but I'm going to speak to it. Oh, there we are. So this is the new book I'm working on. When public safety is at risk, we need engineering grade protections. You know, critical networks, the difference is unacceptable worst case consequences. Insurance is something that protects the business. It does not protect public safety. We must not confuse the role of insurance when safety or when critical infrastructure is at risk. So this is some of the topics that are coming in the new book in October, November. Next slide, please. A reminder that the Industrial Security Podcast is available today. You can go to the Waterfall website under the resources menu, or you can just go to your favorite cell phone podcast app and search for Industrial Security. Different guest every episode, showing us a piece of the elephant, going deep on something that they are an expert on. I didn't think the podcast was going to last. We passed our 100th episode. I didn't think there were that many faces of the elephant. I was wrong. I have learned something every episode and am humbled by how much knowledge there is out there. So I would encourage you to tune in and benefit from this. It's not a podcast about Waterfall. It's a podcast Waterfall sponsors as a public service. Next slide, please. A few words about Waterfall. We've been around for 15 years. We're deployed all over the world. We're deployed we're trusted by critical industrial infrastructures and other kinds of manufacturers and processes all over the world. Next slide, please. And, I've been talking a lot about engineering. I gave an example with the bridge that might have sounded critical of IT grade security. It's not. It's complicated. We need engineering. We need cybersecurity. We need different amounts of them in different circumstances. A small shoe factory is a very different animal than a gasoline pipeline. So this is, again, the topic of the new book. The short answer is we need them both. And the gap right now is that nobody's documented these engineering approaches. This is why I find the cyber-informed engineering so very valuable, because finally someone is documenting these things. But we need both. Don't get me wrong. That's what I had for you. Do we have questions backed up?
Yes, Andrew, we do have some questions. Right. So before we take questions from all, let's check what people have asked in the Q&A. Request others to share their questions as well. That would be easy to track. So, so the first question: what are your prediction of attacks for 5 years from now? Do ransomware be taken over by intellectual property or data theft incidents in OT?
Complicated. We only have a couple of years data in the new reality of the threat environment. Some of the attacks, we don't know what they were because the public record doesn't say. There might be a Securities and Exchange Commission filing because companies in the United States publicly traded have to report any thing that happens that might cause an investor to buy or sell shares. So they have to report cyber incidents. They don't say much about them. They say we had a cyber incident. It cost us $6 million. Any questions? Yeah. Was it ransomware? We don't know. So where we have data, most of the attacks are ransomware. Where we have data, hacktivist activity has been increasing from 5% to last year 10% of the total where we have data. Is that a trend that's going to continue? We don't know. We only have 2 data points. But there was another question about Intellectual property theft. That is not something that I'm tracking. Our report does not look at intellectual property theft. That's a problem for the IT people. This is another reason we need IT grade protections, especially in discrete manufacturing. There are fewer trade secrets in coal-fired power plants than there are in aircraft manufacturing. So we do not count those incidents. They are important incidents. We need cybersecurity to protect information in manufacturing facilities, in addition to needing network engineering and security engineering to protect safety in those networks. We need them both.
Right. So the next question, your slides on cyber incidents resulting in cyber physical impact seemed a comprehensive list of incidents impacting business continuity. Is there a source of information for the list of all these attacks that is updated continuously and in public domain?
Yes, the co-author on the report is Greg Hale. He is the editor at ISS Source and the CEO at ICS Strive. So maybe I'll type into the chat. It's there we go. ICS Strive. There we go. So that is the co-author on the report. That's the repository that is keeping track of all of these attacks in as close to real time as Greg can manage.
All right. Thanks, Andrew. The next question from Amit Singh. But again, Colonial Pipeline remains under dispute as a categorization that is IT or OT. What is your viewpoint on this, especially?
There's a lot of people out there arguing, was this an IT incident? Was it an OT incident? And it was ransomware that compromised the IT network with physical consequences. We shut down the OT systems. You know, I look at that debate. Was this IT? Was it OT? I'm going, folks, you're arguing about the wrong thing. Okay, it seems to be, these people seem to be focused on a turf war between whose job is it to prevent that consequence? Is it the job of the IT team or is it the job of the OT team? I suggest the business doesn't care. The business wants cyber threats to physical operations dealt with. And especially when we have these dependencies, it gets really complicated whose job it is. The business doesn't care whose job it is. The business is going to knock heads together until we solve this cyber threat to physical operations. So our report is not focused on IT incidents or OT incidents. It's focused on deliberate cyber attacks that caused physical consequences. It's focused on cyber risk to physical operations, no matter whose turf it falls into.
Right. So next question from Arun. There is a school of thought that implementing unidirectional gateway alone to segregate IT and OT networks is not sufficient and cannot adequately combat cyber physical attacks. What are your thoughts on this in the context of remote access requirements to ICS environment from a network segregation perspective?
So there's two questions in there. One has to do with remote access, and the other one has to do with unidirectional gateways. And let me say, network engineering is a tool. You know, unidirectional gateways are network engineering. It's a tool that's used to increase reliability, to reduce threats to safety. But nobody buys a unidirectional gateway and puts their feet up on the desk and says, there, I'm done. Nobody can get me. Nobody does that. I mean, I can carry an attack. Okay, if I've got a unidirectionally protected site, if I got a site protected by firewalls, if I got a site protected by anything, I can carry attack information into the site in my head. I can carry passwords and malicious intent into the site in my head. I waltz past physical security. I sit down at the first industrial system I find. I type in the password and trigger a shutdown. Did a unidirectional gateway protect me? No. Did a firewall protect me? No. This is why in the Black Book, Chapter 4 talks about offline protections. Chapter 5 and 6 talks about online protections. Unidirectional gateways are engineering grade protection against online attacks, not offline attacks, against online attacks coming through the gateway. Do you still need an intrusion detection system? Yes. What's the most important role of an intrusion detection system? It is identifying when some well-meaning fool puts a Wi-Fi hotspot on the industrial network and bypasses the unidirectional gateway. So no, unidirectional gateways are not magic, but they are network engineering. They are engineering grade protection against online attacks coming into industrial networks through the device. Firewalls can't do that. The question of remote access. Remote access is extremely dangerous. I was impressed by the French ANSI standards, ANSSI. Okay, not the American, ANSI, the French ANSSI standards. They have 3 network classes. They have, called them unimaginatively class 1, class 2, and class 3. I look at it, it's a complicated formula to figure out where you are. They say the formula for class 1 is easy. All business systems are class 1. The formula for class 2 and class 3, because these standards are for critical infrastructure, the formulas basically say safety critical is class 3 and reliability critical is class 2. And they say, look, if you have a connection between a safety critical network, a class 3 network, and a class 2 network, you are forbidden from using a firewall. You are forbidden from any kind of online remote access. It's not allowed. It's too dangerous for the safety system. And if you have a reliability critical network, like a large power plant or a water treatment system for 500,000 people, they strongly recommend unidirectional protection. They strongly discourage. The word, they have an English translation. In the English translation, the word strongly is followed by the word discouraged. They strongly discourage any kind of remote access into the industrial network because it's just too dangerous. Can you do remote access? Yes, of course. Do people use remote access? Sure. The slide I skipped was remote screen view. It's covered in Chapter 6 of the Black Book. The Waterfall distributes the Black Book as a public service. Shipping to India is a challenge, but we will try. If you go on the website under resources, secure operations technology, and request a copy of the book, we will get a copy of the book to you if we can, free of charge. Do we have time to go into one of the examples of remote access? Or
Yes,
how
we
many
can.
questions have we got backed up there?
There are 2 more questions, and
okay.
Yeah.
Then let me digress for just a minute. How can you do remote access on a unidirectionally protected network? The answer is a little complicated. Think about it. To a man with a hammer, all the world's a nail. To a man with a firewall, all questions have the same answer. The answer is open a TCP port. What's the question? How do I get antivirus in? Open a TCP port. How do I get production orders from my SAP server into my refinery? Open a TCP port. How do I get remote access? That's 2 TCP ports, one for the TLS VPN and one for remote desktop. All questions have the same least secure answer. When you look at the customers, you look at the industrial sites that are doing network engineering today, they don't use the same answer for all questions, the same least secure answer for all questions. They use the most secure answer for each of the questions. So when you're looking at remote access for insiders is different from remote access from outsiders, is different from continuous remote access for remote operators. There's lots of different scenarios. Each of them has a different solution. So let's take the classic example, which I talked earlier with EPRI, which is turbine management. When the turbine vendor, when their artificial intelligence says there's a vibration anomaly building up, we're going to see a catastrophic failure in 6 weeks. So we should adjust the turbine right now so that we can delay maintenance not 6 weeks from now or 5 weeks from now, but we can delay it by 6 months or 2 years because it saves money. That person at the vendor picks up the phone, calls the site, and says, you've got a problem on generating unit number 3. Can I have an hour on Thursday at 3 o'clock to fix it? And the site says, sure, and books it. 3 o'clock Thursday comes, an engineer sits down at the vibration workstation, calls up the vendor. They know who they're calling. The vendor, says to the vendor, you ready for this? The vendor says, yep, and activates remote screen view and starts taking a picture of the screen of the much like you're seeing, a picture of your screen here. John and Puneet, you're seeing a picture of the screen, takes this picture of the screen, sends it through the strange one-way hardware and stands it up on a website on the outside. And now the vendor logs into the website, they can see the screen, they can say, okay, but the vendor can move their mouse all they like. They can bang on the keyboard all they like. It's not physically possible for any of those signals to get back into the industrial network. So the vendor has to say over the phone, okay, bring up the vibration diagnostics, and they can see the mouse move, and they can say, no, that's system diagnostics, 2 further down. There you go, that's vibration diagnostics. And they can work together to solve this problem, to adjust the turbine, to delay maintenance. The vendor sees the process as supervising the site in the course of a complex correction to make sure it's done according to the vendor's processes and procedures. The site sees the process differently. Whose turbine is this? The engineer moving the mouse is not a mouse monkey. Okay, the engineer is responsible for the correct operation of the turbine. If the turbine shakes itself to pieces, it's on the engineer's head. It's the engineer going to get fired, not the vendor. So the engineer wants to know why, wants to know what the vendor is doing to my turbine, and is supervising the vendor, is taking notes, is asking questions, is going to move the mouse only when that engineer knows that it's the right thing to do to this turbine at this time. Each of them thinks they're supervising the other. Remote screen view meets both sets of needs. It's the right solution when you have an outsider. Why is the vendor an outsider? Well, has the vendor been through the criminal background checks for the site? No. Might have been through the vendor's criminal background checks, but we don't have access to them. Has the vendor been through the site's safety training and awareness? No. Has the vendor been through the site's security training and awareness? No. This is an outsider. We need to supervise outsiders when they come into the site. This is the right solution for outsiders. There's a different solution for insiders. There's other solutions for other scenarios. They're all documented in Chapter 6. So that's a long answer. No, nobody puts their feet up on the desk when they buy a unidirectional gateway and says, there, I'm done. That's just silly. And yes, there are remote access solutions, and they're going to be a little bit unusual from anyone who's familiar with, VPNs and remote desktop. Going to be a little bit unusual because VPNs and remote desktop, bluntly, are dangerous. And we need different solutions if we're going to get into sensitive networks.
Right. Okay. There are a couple more questions, and there are 3 people who would like to speak directly and ask a question. So Chirag is asking, is there a VM available for the appliance?
So we're talking about the Waterfall unidirectional solution.
Yes, that's right.
First off, where to begin? Virtual machines are a touchy subject. They're used increasingly extensively on OT networks. What you have to be careful of is not to mix IT and OT virtual machines on the same hypervisor, the same host, because then all you've got separating them is software. You need separate hosts, one on the IT network, one on the OT network for these virtual machines. Once you've done that, now it makes sense to put a unidirectional gateway between them. And the gateway hardware is hardware. Okay, you cannot get engineering grade protection out of software. All software has vulnerabilities. All software can be hacked. I mean, I wrote software for 20 years. I did not try to put bugs into my software, but in spite of my best efforts and the best efforts of all of my colleagues and all the teams that I ever led, every piece of production grade, high quality software we produced had bugs. And some of those bugs were vulnerabilities. So if you need engineering grade protection, you must use hardware, not software, not just software. But to the question of if we have the engineering grade hardware, can we host the software that makes copies of things on virtual machines? The short answer is yes. We do have people hosting the software. It's a little bit tricky because your network connection to the hardware has to be extremely reliable. But our solution architects can walk you through the process of configuring your hypervisors so that we get the required reliability.
All right. Okay. Deep is asking how to control and support will happen if we are using a unidirectional security device from control center or data center. Is this unidirectional security device will work as a firewall? I guess you partially answered this,
I
but
did, yeah.
yeah.
So let me say, first off, the gateway is not a firewall. What are firewalls? Intrinsically, firewalls are routers. Um, yes, they've got a whole bunch more software, but fundamentally, firewalls, like a router, forward messages from one network to another through the device. The gateways never do that. None of the messages on the industrial network make any sense on the IT network. What does the gateway do? It sends small questions to the data source. Please give me everything that's new. Gets a large answer, 30 megabytes back. Here's everything that's new. On the other network, makes a large command, insert all of this stuff into Pi, and gets a small answer. That worked. What next? Completely different conversations. And so the gateway is not a firewall. And there are remote access mechanisms, but they're more complicated than open two TCP ports, one for the VPN, one for the remote desktop. I'm happy to talk to people offline. I've got a whole session on remote access a couple of years back on the Waterfall website, and it's all there in chapter 6.
All right. Amit would like to share a question. Amit, you can unmute yourself and ask the same.
Yeah. Good evening, Puneet and John, as well as to Andrew. First of all, thanks for organizing such a nice session. And really, Andrew, first time I listen fully more than 1 hour. And other than question, I would like to say something. That's why I raised my hand. Basically, the two specific things in your explanation, really, which is again, there is discussions, C has op and blah blah. But what you say, the engineered protection, you can say the physical protection, that is really very important. And the engineers who are working in the OT world, what is the top event and what is the ultimate protection? And be it because being work in petrochemical refining, we have seen a lot of reactors things. So uh, uh, there are relief valve, there are other physical protections. So this is very important consideration, because a lot of focus is how to harden the OT and how to do. But then, as you rightly say, during the detailed design and life cycle, even we do jobs, we do re-verification, a lot of things we do. But then while doing the next time, are the main challenges in this remains is the maybe the existing assets. Of course, new assets still people are moving in different direction. But yes, it is very important aspects, and I think that's what you explained. You are already going to cover in some of your book. It will be very interesting. But as a OT, as an engineer, I wouldn't say the OT engineer, but even the control system engineer or as a ownership, this becomes quite important how we are looking the cybersecurity. So the physical protection and way of engineering is equally important. While next time doing the re-verification of a job, need to think, what if even the breaches happen in the ESD system, emergency shutdown or control system, and somebody is trying to play with some parameter, be it pressure, label, temperature, whatever. Of course, then what is the worst case scenario and how it is protected physically? So that is one thing which really and second thing is you explained something regarding the it is more on the container moment, but for me, being working with logistics management system with a chemical manufacturing process, I would see, I think you are talking more on the MES part, manufacturing execution system, which is also handling the inbound and outbound logistic. So yes, and this discussion happened 2-3 years back while we thought of what will happen, because we are doing all the inbound and outbound logistics management through MES. Of course, there is a control system and SAP all interacting. And what if this is failed? And then what is the fallback scenario? It took, I would say, almost 15 days to come out with fallback, that even if 1 day, 2 day I have to manage, then how I am going to manage it actually. Which is again a concept which we had not realized, but it is again coming, what is the fallback scenario in such cases. So again, it was not a question, but I think it was very insightful, and thank you very much for giving such a bold presentation. And certainly we would like to expect more interaction in future with you, along with support of Puneet, John. Thank you very much.
Thank you, Amit. Right. Yeah.
Thank you.
Yeah. So, yeah, you can mute yourself, Amit. Chitrang, you can unmute and share your question quickly, but shorter question.
Yeah,
Chitrang?
sure. So,
Yes,
yeah,
go
hi,
ahead.
hi, Andrew. Thanks for this session. I have one query on the technical implementation of the unidirectional gateways. For example, as you understand, in a complex refineries, there are multiple OT networks and with different network topologies, different network IDs. So, how to implement a data diode or a unidirectional gateway in certain scenarios? I mean, because different networks have a different network IDs. Is it possible to have a single data diode kind of thing for all the multiple networks?
Short answer is yes. Refineries are massive. I visited a refinery that was 2 square miles, 3 square kilometers, and that's a small refinery. That refinery had 6 networks in it. A large one is going to have 20 or 25 networks in it. Almost all refineries that we serve have one unidirectional gateway between the OT network and the IT network. And so what that means is you've got firewalls, you've got a firewall, you've got, it means there's still a lot of firewalls inside the industrial network. And you connect those networks with firewalls to the IT network. Well, instead of connecting them to a DMZ in the IT network, now connect them to a DMZ on the OT network and put the gateway on the top of that DMZ reaching out to the IT network. This is what we see almost everyone do. And so the gateway protects all of physical operations and all of, so don't get me wrong. I'm not saying, oh, whoever's got, yeah, if you could go on mute, please. Thank you. I'm not saying replace every firewall in the industrial network with a gateway. That doesn't happen. Use firewalls inside the network where all of the consequences of compromise are the same. They're safety critical. Inside the safety critical network, the extended OT network, not just the safety instrumented network, the whole OT network. Use firewalls. On the IT network, use firewalls at the boundary, at the consequence boundary. This is what network engineering is saying. You need something stronger. This is what the TSA is saying. You need something stronger at that consequence boundary. You can't just do the same thing you do everywhere else. This is where CIE is starting to say, we probably need something stronger, but they're still working on it. This is where my book is saying we observe our customers doing something stronger at that boundary, not everywhere, at that boundary.
Right. I hope that answers your questions, Chitrang. Hardik, You can unmute yourself and ask the question.
Yeah. Hi. Hello, Sir Andrew.
Hello.
So, yeah. My question is related to, I have worked on a Foxit data diode while I was pursuing my masters. At that time, I've seen that, emulating the scenarios and doing such scenarios and maintaining cybersecurity at the both the end. Like, if we have, unidirectional diode in the one place, and if we see OT security is becoming mature day by day, but threat detection and patch management and such things are still missing, and or people are adapting such things. So, do you have anything in your solution which is going to help in this particular regard, or it is we have to go for another solutions?
No, we have Waterfall has partners in that space, and yeah, I agree completely. Again, nobody puts a gateway in and says, "There, I'm done." In particular, there's still all of the ways that you can physically carry attack information into the site. You can carry it into the site in your brain, as I gave in my example, on a USB drive, in a cell phone, in a laptop being carried in. All of these mechanisms need to be dealt with. And sometimes you cannot eliminate completely all of these ways that information is leaking, potentially attacking your systems. And so where do you use IT security in the OT network? How do you use it? The short answer is those systems in your OT network that are the most exposed to these offline attacks are the systems where you need to use IT security most aggressively. And it's more complicated than that because risk comes into the equation. Who's coming after us? Is it a nation state who's got sleepers in our employee base? Is it disgruntled employees who don't know much about security? This is the topic of several chapters in the new book. So it's complicated, but the short answer is that no, you still need IT security. You still need to detect, respond, and recover. And you need to do so most aggressively where the OT network is most exposed, in spite of the safety engineering, the protection engineering, the automation engineering, and the network engineering grade solutions that you've put in place. In spite of the engineering solutions, if you're still exposed, when you're still exposed, that's where you have to use IT security the most aggressively. You don't have to use it everywhere aggressively. It's really expensive using IT security aggressively in an OT network, but you do have to use it where you're most exposed.
Agreed. Thank you. Thank you.
Right. I think that's the end of questions. I hope it was a very interesting and informative session, Andrew. Thank you for joining us today, spending your morning with us in your busy schedule. And thank you everyone for joining us on a weekend evening, and I really appreciate it. So we have an upcoming session on Security Operations Center. There's always a debate: is it IT SOC, is it OT SOC, or is it just SOC? So there is also going to be a panel discussion and very engaging and lively debate. We also had one in group, but this is going to be on the next level. So for more updates, follow us on the LinkedIn, join us on the WhatsApp. And Puneet, you have something to say?
So thank you, Andrew, for such an insightful session. And we would like to have some more sessions from you. And
thank you.
As we are going to have a SOC Security Operations Center session very soon. So we would like to invite you as a panelist. Would you be interested to join as a panelist for that?
I am always happy to join. We'd have to talk about my direct experience with SOCs is over 10 years old. I left that world when I left Industrial
Defender. Just wanted to see the perspective, because when you see the threats, you see the incidents. How you see that, whether we should have a single SOC for OT and IT, or we should have a separate SOC. So we are preparing for that. So we'll be going to have that session very soon. Okay.
Sure, I'd be happy to join you. Let's figure out the timing though, because I'm on the road a bit.
Yes,
sure. And thank you everyone for joining. And we very soon we are also going to have our own website. So you can have all those events and everything available on that our website very soon.
Yeah.
Great.
Okay.
Thank you.
Thank you.
Thank you once again. Thank you, everyone.
Bye.
Have a good weekend. Have a good day. Bye bye. See you
Have a good
next
day.
time.
Bye. Don't forget to
Thank
fill
you,
the
everyone.
feedback form. Thank you.